you and the finish line, so I will be try to be brief. Okay, so this is joint work with my PhD student Nikhil Mande at TIFR. So this talk is about understanding, or some sort of frustration about understanding depth 2 threshold gates. So let me just start with the simple definition. Remind you, we have seen a lot of things about linear threshold gates in this workshop, especially last afternoon. So this is a linear threshold gate where we have the inputs, and these inputs feed into this gate with various weights, and these weights are typically unrestricted, so you can think of them as real numbers, or equivalently you can think of them as integers, and then they could be exponentially large. And then there is in general there's an activation function, which in our case would be the step function. So that's the linear threshold gate. And this, I don't have to tell to this audience the importance of this, especially in these days of machine learning. So we understand a lot about this from early on. In this workshop, we would like to understand what it can't compute. And if you think about it, it's not hard to see that the cardinal example of what such a gate cannot compute would be the parity function, because the parity is very nonlinear, sort of wiggles down. If you symmetrize parity, look at its spectrum, it's always changing its sign, and something like a linear function of course can't do it. So formally speaking, the sign degree of the parity function is omega n, which means that any polynomial which wants to sign represent the parity function requires full degree, any multilinear polynomial over the Boolean cube. And the linear threshold function of course has sign degree 1, so this is a famous theorem due to Minsky and Papert from long back, and this shows that parity is not an LT1. So I'll represent, my notation here will be, well, we'll have depths of linear threshold circuits. LT1 just means depth 1 and polynomial size. So we understand this, so that's satisfying. Now let's go to depth 2 networks. So just a very natural problem. Now instead of having just one layer of linear threshold gates, we have 2 layers of linear threshold gates. Question is again, what can it not compute? Seems like a very basic question. It doesn't take too much time to realize that now you can compute functions with high sign degree like parity, in fact in linear size, and in fact you can compute all symmetric functions. You can compute iterated addition and other interesting functions. And as I said, I will represent these kind of circuits with LT2, which means polynomial of threshold. So the question is, what can't these functions compute? Can they compute multiplication of 2 integers, division? Well, we don't know. We even don't know whether if satisfiability can be computed efficiently by these networks. And this seems like a really, really basic problem. I mean, just depth 2 linear threshold networks, we have no explicit lower bounds, not even next. So, well, I mean, don't feel too bad about it. The purpose of my talk is to possibly give some reasons why this might be non-trivial to do. So let's see what happens if we restrict weights. Since we can't compute unrestricted depth 2, we can't understand the power of unrestricted depth 2 linear networks. Let's try to see what happens if we restrict the weights of each gate.
Sorry, the threshold gate, the theta in the threshold gate is always the step-up function, or is it some...
Sorry?
So the threshold gate is just the usual threshold gate, or we have this step-up function, theta?
Yeah, it's always the step function. In this talk, it's always the step function.
Yeah, but the thetas can be different.
The thetas can be different, yeah. The step can shift. So what happens if we restrict weights? Well, let me first convince you that restricting weights does make life easy. For example, here are basic half spaces or linear threshold functions. This is equality, which just checks whether 2 n-bit strings x and y are equal, and you can write it in as a sort of a linear equation, of course with large weights. Okay, and this other function is the very familiar function greater than, where we want to check if x is greater than or equal to y. X and y are again n-bit integers, and you can write it in this way. So this is an exact threshold function because we want to check for exact equality, and this is the usual threshold function. And what we know from basic communication complexity is that the communication complexity of both these functions greater than an equality is omega n. There is a variety of ways of proving it. You can consider the rank of these matrices, the Boolean matrices. They are full rank, and therefore the communication complexity is full. Whereas if you look at a majority gate, now a majority gate you can think of, for this talk it wouldn't matter, you can think of as the weights being 0, 1, or you can think of the weights being just some polynomially bounded number, integer. So the communication complexity of a majority function is order log n. And so that's one way of arguing that these functions cannot be represented by low weights. So weights can help. And therefore, so I will introduce this other notation. Bear with me. This is the last one. So this hat would mean the corresponding circuit where every linear threshold gate is restricted to have polynomial weights. You may think of them as just majorities. Okay, so in depth 1 we have a separation by a simple argument. So let's now look at more depth, and in fact it will turn out that there is actually sort of a rich hierarchy from depth 1 to depth 2. For that, let me introduce this function inner product, which is, I don't have to tell this crowd what it is. It's just the standard scalar product of two n-bit strings, and then I mod it out by 2. An important result again from long back due to THRO and Goldreich is that this function's communication complexity is extremely hard, in the sense that even if you want to sort of do slightly better than random guessing, as large as like 1 over 2 to the little o of n, you have to communicate a lot, omega n bits. Okay, so this is a classical result, has been very influential, and what is its consequence for us? The consequence is the following. Now, if I look at depth 2 networks where I have restricted all the gates to have small weights, they are majorities, okay? We will see that such circuits cannot compute the hard function inner product, and it's actually a very simple argument, but very nice, which is that I will say that the communication complexity of whatever function here computed is small. Why so? Because Alice and Bob, what they can do is Alice can sample a random sub-circuit feeding into this top gate, and then send it over to Bob. Here I'm assuming that we have private coin randomness, which will be convenient for this talk. And this will require log s bits to be transmitted to Bob because the fan-in of this top gate is s. And then, Alice will just tell Bob the number of ones that she sees on her side. And then Bob can compute the value of this sampled gate. And it's not hard to see that with good probability, the protocol will be right, in the sense that you will do 1 over 2s better than random guessing, right? So if s is small, like polynomial, or even just slightly sub-exponential, you get sub-exponential advantage over random guessing, whereas the amount of communication is still much smaller than n. Okay? So this means, therefore, that IP cannot be computed by small size majority of majority circuits because of the THRO-Goldreich strong bound that I talked about. Right? Okay, so now what are the known limitations of depth 2? This tells us that this result that I alluded to was due to Hainal et al. From 87, which showed that IP needs to do the omega n size, and this is a discrepancy argument. So the question is now, what happens if I look at majority of threshold circuits? In fact, if you go back to the previous argument, you could do the same thing there without any loss. But what is surprising is that in this sort of important work due to Goldman, Hastad, Rasborov from 92, they showed that these two classes turn out to be exactly the same. They're just within a polynomial factor apart. Okay? And this is sort of quite interesting. So it seems like if you add weights at the bottom, it does not matter. Okay? And in the same paper, they also showed that if you add weights at the top, it does matter, meaning there is a function in threshold of majority. Here, this threshold is unrestricted. Everything else is restricted. to have small weights, then this class is strictly more expressive. It can compute functions that are hard for majority of majority. So now we have the following weight hierarchy. So as I said, the greater than function separated these two. This was separated by parity. Then surprisingly, Goldman, Hastad, Razborov shows that these two classes are the same. They also show that this is strictly contained over here. This class is strictly contained in threshold of majority. And at that time, this was not clear, except the containments. Even the containment needs an argument to be shown to argue that why this is contained in weight restricted depth 3, and that was again shown by Goldman, Hastad, Razborov. So the question is threshold of majority in LT, read this as LT3 hat, is it in LT3 hat? And the other question, that's the first question, the other question is, do weights at the bottom ever matter when you're dealing with depth 2 circuits? Okay. So here's how one would argue about threshold of majority. Let's go back to the same setting. Let's look at this slightly different communication. The communication protocol is going to be almost the same. Alice and Bob now want to compute, again, this function. Now, instead of uniformly randomly sampling a subcircuit, what Alice does is she looks at the probability distribution induced by the weights of the top gate. That's a natural thing to do. And then she samples a subcircuit proportional to this probability distribution and sends it over again to Bob. Okay? So the communication is precisely the same, the total cost. However, now the advantage that she gets, that Alice and Bob get, could be substantially lower. Right? These weights could be very large. And so all you know is like, it's just 1 over the sum of the weights advantage, which could really be small, but it's non-zero. So you do get a right answer with just barely beating the random guess probability of half. And now we will consider, this brings to my the main topic of my talk now is we will consider such protocols which seem extremely relaxed in the sense that you need to do barely better than random guessing, okay? Just greater than half, strictly greater than half, otherwise all bets are off. And this protocol was also, this class of protocols are called UPP protocols. They are the analog of the PP class in Turing machine, complexity, and this was introduced by Paturi and Simon back in '84. And so what we show is that what this implies is that if a function has small sized threshold of majority gates, then at least these class of protocols can compute such functions efficiently. So how do we prove lower bounds against such protocols? They seem to be very, very powerful. So the first question to ask is IP in UPP? And this brings us to the notion of sign rank. So this is a very nice notion. Turns out to be completely equivalent to having efficient UPP protocol. So what's the definition of sign rank? So if I take any non-zero matrix, M, it's the minimum rank needed by every real matrix to represent it in a sign honoring way, meaning every entry of my new matrix A in sign must be exactly the same as the sign of Mij. And so the smallest rank such matrix A would be called the sign rank. So it's kind of a rigidity kind of notion, except that normally when you consider matrix rigidity, you don't have to, you only allow perturbations at a few places, and those perturbations need not be sign honoring. Here you're allowed to perturb at every point, but you have to maintain the sign. And what Paturi and Simon carefully and very beautifully observed is that the unbounded protocol complexity, unbounded error complexity of any function f is precisely equal to the log of sign rank of the communication matrix of f. To motivate sign rank and to get a better perspective, let me look at it slightly differently from a geometric point of view. So sign rank has also been considered in other contexts, in learning theory and other places, where it's called the dimension complexity. And why so? So let's look at this matrix. So this is just a 4x4 matrix which mimics the greater than upper triangular matrix. So I've just filled it with all ones at the top and minus ones at the bottom. Now its rank is 4, and in general if I have a 2 to the n by 2 to the n such matrix, of course its rank would be 2 to the n. But let's look at its sign rank, and geometrically I want to place a set of points and hyperplanes in some Euclidean space, such that this, by looking at the way the hyperplanes partition the set of points, I should be able to get back my target matrix. So in this case, I just place these points on a line in two-dimensional Euclidean space, and of course these are the hyperplanes that are shooting through the origin, and it's not hard to see that if I take the product of these points and hyperplanes, this exactly represents in sign this matrix, right? And this is just in 2 dimensions. So no matter what the dimension of this matrix was, such a matrix has sign rank, somewhat surprisingly, only 2. Okay, so the greater than function, therefore, in general, would have sign rank 2, which was a hard function, at least for deterministic communication complexity, and even for randomized requires log of n, now requires just roughly 2 bits of communication in this powerful unbounded error model. So let me look at one last example very quickly. Now the equality function, likewise you can place points. I have placed it in 2-dimensional space, but in 2-dimensional space, again, you place it on a circle and you can separate them, but I need these hyperplanes to sort of go through the origin, so that's why I'm thinking it of as, it's like the cross section. It's in 3-dimensional Euclidean space, and therefore the sign rank of equality will be 3, and you can show that you can do no better. So sign rank of equality drops down to 3. Okay, so equality has, again, very small sign rank by itself. Okay. So for a long time, it was not, it's not immediately clear why, in fact, any function should have large sign rank. And this result, due to Allon, Frankel, and Rodel, about a year after the Paturi-Simon paper, showed quite non-trivially that there are, at least for random functions f, the sign rank would be maximal. Okay? And this requires some deep theorem from algebraic geometry. So after a long time, Forster made a real breakthrough when he was able to show an explicit function, namely the inner product function, to have, again, very close to maximal sign rank. More interestingly, what Forster was able to show is a very nice spectral condition that would allow you to lower bound sign rank. What he showed was that if M is such a sign matrix, n by n, then its sign rank is at least n by the operator norm of n. And if you look at a function like inner product, which is like a Hadamard matrix, it has, you immediately get that the sign rank is going to be 2 to the n, 2 to the n by 2, and this would give you show you that the UPP cost of computing inner product is very large. And this is really surprising. So because even if you allow it to err just to barely better than half, you have no choice but to basically communicate n bits. And this shows that, by the connection that I showed before, that IP needs 2 to the omega n size threshold of majority circuits. Okay, so let's look at our updated weight hierarchy. So here we are. Threshold of majority is now strictly contained in LT3, because inner product, if you think about it, it's a simple observation that you can do it in depth 3. Okay. So now we are left with this sort of question. Well, we can't prove a lower bound for LT2. Yeah, this is a frontier. We don't understand how to prove a lower bound, but maybe threshold of majority is the same as LT2, and then we have a lower bound. In fact, it was interesting to note yesterday's talk that as far as satisfiability algorithms are concerned, they seem to be algorithmically the same. Okay, so maybe threshold of majority is just the same as LT2, and it wouldn't be surprising because of this nice result due to Goldman, Hastad, Razborov, who showed that majority of majority is the same as majority of threshold. So it's feasible that adding weights at the bottom do not matter. And this was asked as an open problem first by Amano and Maruoka in 2005, and then by Hansen and Podolsky in 2010. Well, it turns out that they are not. This is the main result of our paper, which shows that there is a function in threshold of threshold, and it will turn out to be involve equalities, and it's a very simple function that has very large sign rank and therefore is not in threshold of majority. Okay. So that's the new result, and here we need, I haven't yet specified the function, but I'll do so very quickly. It has large sign rank, and just a quick survey of some past work on sign rank. How much time do I have?
Like 1 minute.
Oh, really?
No,
We
started late.
So maybe 5 minutes?
5 minutes.
Okay. So let me skip this. So let me just tell you how we got to this function. So a natural candidate in depth 2 would be to look at, the hardest function, the hardest threshold is this universal threshold. And if you look at a universal threshold on n square log n bits, by just setting the bits, you can simulate every threshold, right? So a natural candidate is, if anything is hard, it better be universal threshold of universal threshold. But this is the problem that typically you face when you are proving lower bounds, that it's not a nice function. I mean, the only handle that we have for proving sign rank is due to Forster, and to analyze the spectral property of such a function is not clear how to go about it. So we want to make it something more structured, and let's go back to the communication game that showed that threshold of majority has small sign rank. So there what was happening was, you were sampling a sub-circuit, okay, and then sending, Alice and Bob were jointly computing that sub-circuit. Now, the minimum thing that you need, if I have threshold of f and I want to have large sign rank, so I want to prevent a UPP protocol from computing this function easily, is that the deterministic complexity of this function should be large, right? Because if the deterministic complexity of this function is small, I will still have an unbounded error protocol. And this immediately sets a natural question. Well, the cardinal function that we have, which has large deterministic complexity, is equality, right? So one would expect the threshold of equality would have large sign rank. It doesn't seem like the naive protocol would be able to do that. It turns out that this threshold is also, if I again give a general threshold, I don't know how to analyze the spectral properties of threshold of equality. So we look at something much more structured, which has been looked at in the 90s, starting from the work of Richard Beagle, a lot of times, especially in the approximation theory literature. This is the nice function called odd max bit, which basically outputs 1 if the leftmost, so I've written here is -1, if it outputs -1 if the leftmost one is at an odd index. Okay? So this you should think of as like a decision list. Okay? This can be simulated easily by a decision list. So anyway, it just outputs -1 if the leftmost one is at an odd index. So if the first index was 1, it outputs -1. If this was 0 but the second index was 1, then it would output 0, and so on. Okay? So it's not hard to see that this is also a linear threshold function with large weights. Okay? And it turns out this provides us with the right structure, so we look at odd max bit of equality. Okay? This is, again, not hard to see that this is in threshold of threshold. Well, odd max bit is in threshold. Equality is an exact threshold, and I leave it as an interesting exercise to show that a threshold of exact threshold is in threshold of threshold. It also is in AC0. Okay, this function is very simple. It's in AC0 as well as in threshold of threshold. And it turns out that this function has very large sign rank. It has 2 to the n to the 1/4 sign rank. So this shows, this gives us the separation. Let me skip a little bit and just maybe in 2 minutes tell you about the communication complexity implications. So the communication complexity implications were observed by Mika, and who kindly pointed us out that it solves one of his open problems. So a long-standing open problem in communication complexity due to Babai, Frankel, and Simons is to prove lower bounds for the polynomial hierarchy, which is like AC0 of rectangles. Right? It's very closely related to matrix rigidity. So this problem has been open for a long time. A much simpler problem is to even show lower bounds against the depth 2, the second level of this hierarchy. Razborov and Sherstov in 2009 showed that this is already very hard because this contains functions of large sign rank. Okay, sign rank in communication complexity is the strongest tool that we have to prove lower bounds. So this was the communication complexity landscape, which due to the work of Razborov and Shestov showed that the second level of the hierarchy, there is a sort of a sign rank barrier because this has functions of large sign rank. And then there is this class P to the MA. So everything below this, we have lower bound techniques, but P to the MA was not known to have large sign rank. However, we had no technique to prove lower bounds. In fact, P to the MA was possibly not even looked at before our work because there was no reason to look at it. So the point is, there was somewhere between P to the NP and the second level, the sign rank barrier, where did it start? It was not clear. Okay. And it turns out that the function that I've talked about, it actually has a P to the MA protocol. And it's a very simple protocol. First thing to notice is there is an MA protocol for OR of equality. Why? Because if you have an OR of equality, Merlin can point out which equality is 1, and then Alice and Bob can confirm using probabilistic verification because equality has small randomized communication complexity. So OR of equality is in MA, and using that and binary search, you can sort of find out the first equality that is 1, right? You can repeatedly do this, use OR of equality as an oracle, keep on finding whether it's in the right half. If it is not, then you move to the left and so on until you find the first position where the first equality, which is 1, and then you know whether it's odd or even. So there's a very simple P to the MA protocol using binary search. So P to the MA, therefore, has this function, and what we have now as an update to the landscape is that, well, there's a reason why P to the MA seems to be a class for which we have no lower bounds, because the sign rank barrier sort of comes down here. Okay, and it sort of just seems, as Mika pointed us out, that P to the MA is just tantalizingly out of reach because we have lower bounds against MA. Okay, and we also have lower bounds against P to the NP. There are multiple ways of proving lower bounds against P to the NP. So P to the MA, if you try to relax it just a little bit, whichever way you do naturally, you have lower bounds. So P to the MA seems to be the right place where lower bound techniques stop because we have this, and the explanation perhaps is because we have large sign rank. Okay, and let me just, there's no time for this. So let me just mention some open problems. Well, of course, this remains the main problem that we started with. Unfortunately, we still have no idea how to prove lower bounds. But I think what is interesting is that this class, decision list of exact thresholds, comes out here as a natural class. Well, I've changed equality to exact threshold because although decision list of equality has large sign rank, but it's an AC0. So we can apply random restrictions, of course, and prove lower bounds. But this is the smallest class which seems to be resistant to random restrictions and has large sign rank. Two important techniques. So if you do bottom-up lower bound, the main technique that we have is random restriction, which this circuit class seems to be immune to. If you do top-down, then we see the strongest technique seems to be sign rank, and we know that this class also has large sign rank. So it would be interesting to prove that inner product, for example, has no such small circuits. One surprising thing I want to point out is if you paid attention to Mina's talk, if you replace this E by just THR, a threshold, then it turns out that you can actually prove lower bounds for this class. So somehow exact threshold makes it hard and has large sign rank. And the other thing is maybe this, so we were able to show that it has large sign rank, but maybe it does not have full sign rank. So you can prove an upper bound on the sign rank, it cannot be maximal, maybe it's 2 to the sublinear something. Since inner product has maximal sign rank, that would also be enough to show that this can't compute inner product. Okay? And in general, it's not clear why threshold of threshold should have maximally large sign rank. So that might be one way of proving lower bounds. And the other target is to, if you're interested in communication complexity, is to prove lower bounds against P to the MA protocols. Okay, I think I'm out of time. Thank you.
I'm afraid that the time is now after 4. So let's thank Arkadev once more.